Charles Steinmetz. Radiation, Light, and Illumination. Lecture 1. Nature and different forms of radiation. 1. Radiation is a form of energy, and, as such, can be produced from other forms of energy and converted into other forms of energy. The most convenient form of energy for the production of radiation is heat energy, and radiation, when destroyed by being intercepted by an opaque body, usually is converted into heat. Thus, in an incandescent lamp, the heat energy produced by the electric current in the resistance of the filament is converted into radiation. If I hold my hand near the lamp, the radiation intercepted by the hand is destroyed, that is, converted into heat, and is felt as such. On the way from the lamp to the hand, however, the energy is not heat but radiation. And a body which is transparent to the radiation may be interposed between the lamp and the hand and remains perfectly cold. The terms heat radiation and radiant heat, which are occasionally used, therefore are wrong. The so-called radiant heat is not heat but radiation energy, and becomes heat only when, intercepted by an opaque body, it ceases to be radiation. The same, however, applies to any radiation. If we do not feel the radiation of a mercury lamp or that of the moon as heat, while we feel that of a coal fire, it is merely because the total energy of the latter is very much greater. A sufficiently sensitive heat measuring instrument, as a bolometer, shows the heat produced by the interception of the rays of the mercury lamp or the rays of the moon. The most conspicuous form of radiation is light, and, therefore, it was in connection with this form that the laws of radiation were first studied. 2. The first calculations of the velocity of light were made by astronomers in the middle of the 18th century, from the observations of the eclipses of the moons of Jupiter. A number of moons revolve around the planet Jupiter, some of them so close that seen from the Earth they pass behind Jupiter and so are eclipsed at every revolution. As the orbits of Jupiter's moons were calculated from their observations by the law of gravitation, the time at which the moon M should disappear from sight, when seen from the Earth E, by passing behind Jupiter, I, figure 1, could be exactly calculated. It was found, however, that sometimes the moon disappeared earlier, sometimes later than calculated, and the difference between earliest and latest disappearance amounts to about 17 minutes. It was also found that the disappearance of the moon behind Jupiter occurred earlier when the Earth was at the same side of the Sun as Jupiter, at A, while the latest disappearance occurred when the Earth was on the opposite side of the Sun from Jupiter, at B. Now, in the latter case, the Earth is further distant from Jupiter by the diameter ASB of the orbit of the Earth around the Sun S, or by about 195 million miles, and the delay of 17 1/3 minute thus must be due to the time taken by the light to traverse the additional distance of 195 million miles. 17 1/3 minutes are 1040 seconds, and 195 million miles in 1040 seconds thus gives a velocity of 195 million over 1040, or 188,000 miles per second. Later, the velocity of light was measured directly in a number of different ways. For instance, let, in figure 2, D be a disk perforated with holes at its periphery. A lamp L sends its light through a hole H0 in the disk to a mirror M located at a considerable distance, for instance 5 miles. There the light is reflected and the mirror is adjusted so that the reflected beam of light passes through another hole, H1 of the disk, into the telescope T. If the disk is turned half the pitch of the holes, the light is blotted out, as a tooth stands in front of both the lamp and the telescope. Again turning the disk half the pitch of the holes in the same direction, the light reappears. If the disk is slowly revolved, alternate light and darkness will be observed, but when the speed increases so that more than from 10 to 20 holes pass per second, the eye is no longer able to distinguish the individual flashes of light but sees a steady and uniform light. Then increasing the speed still more, the light grows fainter and finally entirely disappears. This means when a hole H0 is in front of the lamp, a beam of light passes through the hole. During the time taken by the light to travel the 10 miles to the mirror and back, the disk D has moved, and the hole H1, which was in front of the telescope when the light from the lamp passed through the hole H0, has moved away, and a tooth is now in front of the telescope and intercepts the light. Therefore, at the speed at which the light disappears, the time it takes the disk to move half the pitch of a hole is equal to the time it takes the light to travel 10 miles. Increasing still further the velocity of the disk D, the light appears again, and increases in brilliancy, reaching a maximum at twice the speed at which it had disappeared. Then the light reflected from the mirror M again passes through the center of a hole into the telescope, but not through the same hole H1 through which it would have passed with the disk stationary, but through the next hole H2, that is, the disk has moved a distance equal to the pitch of one hole while the light traveled 10 miles. Assume, for instance, that the disk D has 200 holes and makes 94 revolutions per second at the moment when the light has again reached full brilliancy. In this case, 200 times 94 is equal to 18,800 holes past the telescope per second, and the time of motion by the pitch of one hole is 1 over 18,800 seconds. And as this is the time required by the light to travel 10 miles, this gives the velocity of light as 10 divided by 1 over 18,800, or 188,000 miles per second. The velocity of light in air, or rather in empty space, thus is 188,000 miles or 3 times 10 to the 10th power centimeters per second. For electrical radiation, the velocity has been measured by Hertz, and found to be the same as the velocity of light. And there is very good evidence that all radiations travel with the same velocity through space, except perhaps the rays of radioactive substances. 3. Regarding the nature of radiation, two theories have been proposed. Newton suggested that light rays consisted of extremely minute material particles thrown off by the light-giving bodies with enormous velocities, that is, a kind of bombardment. This theory has been revived in recent years to explain the radiations of radium, etc. Euler explained the light as a wave motion. Which of these explanations is correct can be experimentally decided in the following manner. Assuming light to be a bombardment of small particles, if we combine two rays of light in the same path they must add to each other, that is, two equal beams of light together give a beam of twice the intensity. If, however, we assume light is a wave motion, then two equal beams of light add to one of twice the intensity only in case the waves are in phase, as A1 and B1 in figure 3 add to C1. If, however, the two beams A2 and B2 are not in phase, their resultant C2 is less than their sum, and if the two beams A3 and B3 in figure 3 happen to be in opposition, 180 degrees apart, that is, 1/2 wavelength out of phase with each other, their resultant is 0, that is, they blot each other out. Assuming now we take a plain glass plate A, figure 4, and a slightly curved plate B, touching each other at C, and illuminate them by a beam of uniform light, as the yellow light given by coloring the flame of a Bunsen burner with some sodium salt, a part of the light B is then reflected from the lower surface of the curved glass plate B, a part C, passes out of it, and is reflected from the upper surface of the plain glass plate A. A beam of reflected light A, thus is a combination of a beam B and a beam C. The two beams of light which combine to a single one, A, differ from each other in phase by twice the distance between the two glass plates. At those points D1, D2, etc. at which the distance between the two glass plates is 1/4 wavelength, or 3/4, 5/4, etc. The two component beams of A would differ by a 1/2, 3/2, 5/2, etc. wavelengths, and thus would blot each other out, producing darkness. While at those points where the distance between the glass plates is 1/2, 1, 1.5, etc. wavelengths, and the two component beams are thus differ in phase by a full wave or a multiple thereof, they would add. If, therefore, light is a wave motion, such a structure would show the contact point C of the plates surrounded by alternate dark rings, D, and bright rings, Y. This is actually the case. And therefore this phenomenon, called interference, proves light to be a wave motion, and has led to the universal acceptance of the Eulerian theory. Measuring the curvature of the plate B, and the diameter of the dark rings D, the distance between the plates B and A at the dark rings D can be calculated, and as this distance is 1/4 wavelength, or an odd multiple thereof, the wavelength can be determined therefrom. The wavelength of light can be measured with extremely high accuracy and has been proposed as the absolute standard of length, instead of the meter, which was intended to be 10 to the -7th of the quadrant of the Earth. 4. It is found, however, that the different colors of light have different wavelengths. Red light has the greatest wavelength, and then in the following order: red, orange, yellow, green, blue, indigo, violet. The wavelength decreases, violet light having the shortest wavelength. If in experiment, figure 4, instead of uniform light, monochromatic light, ordinary white light is used, which is a mixture of all colors. The dark and bright rings of the different colors appear at different distances from each other, those of the violet nearest and those of the red the furthest apart, and so superimpose upon each other, and instead of alternately black and light rings, colored rings appear, so-called interference rings. Wherever a thin film of air or anything else of unequal thickness is interposed between two other materials, such interference colors thus appear. They show, for instance, between sheets of mica, etc. The colors of soap bubbles are thus produced. The production of such colors by the interference of rays of light differing from each other by a fractional wavelength is called iridescence. Iridescent colors, for instance, are those of mother of pearl, of opal, of many butterflies, etc. Light, therefore, is a wave motion. The frequency of radiation follows from the velocity of light, and the wavelength. The average wavelength of visible radiation, or light, is about L of W equals 60 microcentimeters, that is, 60 times 10 to the -6 centimeter, or about 1/40,000th inch. And since the speed is s equals 3 times 10 to the 10th centimeter, the frequency is F equals s over L of W equals 500 times 10 to the 12, or 500 millions of cycles per second. That is, inconceivably high compared with the frequencies with which we are familiar in alternating currents. If, as proven, light is a wave motion, there must be something which is moving, a medium, and from the nature of the wave motion, its extremely high velocity, follow the properties of this medium. It has an extremely high elasticity and extremely low density, and it must penetrate all substances since no vacuum can be produced for this medium, because light passes through any vacuum. Hence it cannot be any known gas, but but must be essentially different, and has been called the ether. Whether the ether is a form of matter or not depends upon the definition of matter. If matter is defined as the hypothetical carrier of energy, and all the information we have of matter is that it is the seat of energy, then the ether is matter, as it is a carrier of energy. The energy of radiation, during the time between the moment when the wave leaves the radiator and the moment when it strikes a body and is absorbed, resides in the ether. 5. If light is a wave motion or vibration, it may be a longitudinal vibration, or a transversal vibration. That is, the particles of the medium which transmit the vibrations may move in the direction in which the wave travels, as is the case with sound waves in air. If in figure 5 sound waves travel from the bell B in the direction BA, the air molecules M vibrate in the same direction, A to B. Or the vibration may be transversal. That is, if the beam of light moves in figure 6 perpendicularly to the plane of the paper, the vibrating particles move in any one of the directions O, A, O, B, etc. in the plane of the paper, and thus perpendicular to the ray of light. In the former case, a longitudinal vibration, as sound, there obviously can be no difference between the directions at right angles to the motion of the wave. In a transversal vibration, however, the particles may move either irregularly in any of the infinite number of directions at right angles to the ray, and thus no difference exists in the different directions perpendicular to the beam, figure 6. Or they may vibrate in one direction only, as the direction B, O, A, figure 7. In the latter case, the wave is called polarized and has different characteristics in 3 directions at right angles to each other. One direction is the direction of propagation, or of wave travel. The second is the direction of vibration, and the third is the direction perpendicular to progression and to vibration. For instance, the electric field of a conductor carrying alternating current is a polarized wave. The direction parallel to the conductor is the direction of energy flow. The direction concentric to the conductor is the direction of the electromagnetic component, and the direction radial to the conductor is the direction of the electrostatic component of the electric field. Therefore, if light rays can be polarized, that is, made to exhibit different properties in 2 directions at right angles to each other and to the direction of wave travel, this would prove the light wave to be a transversal vibration. This is actually the case. For instance, if a beam of light is reflected a number of times under a fairly sharp angle, as shown in figure 8, this beam becomes polarized. That is, for instance, the reflection from the mirror M0, set like the mirrors M1, M2 and so on, which produce the polarization, is greater, and the absorption less than from a mirror set at right angles thereto, as M0'. Some crystals, as Iceland spar, calcium carbonate, show double refraction, that is, dissolve a beam of light, A, entering them into 2 separate beams, B and C, figure 9, which are polarized at right angles to each other. In a second crystal, K2, beam B would then enter as a single beam, under the same angle as in the first crystal K1. If K2 were in the same position as K1, while if K2 were turned at right angles to K1, beam B would enter K2 under the same angle as beam C in crystal K1. 6. As seen, light and radiation in general are transversal wave motions of very high speed, s equals 3 times 10 to the 10th centimeters per second in a hypothetical medium, ether, which must be assumed to fill all space and penetrate all substances. Radiation is visible, as light, in a narrow range of frequencies only, between 400 times 10 to the 12th and 770 times 10 to the 12th cycles per second, corresponding to wavelengths from 76 times 10 to the minus 6 to 39 times 10 to the minus 6 centimeters. All other radiations are invisible and thus have to be observed by other means. I have here a pair of rods of cast silicon, 10-inch long, 0.22-inch in diameter, having resistance of about 10 ohms each, connected in series with each other and with a rheostat of about 40 ohms resistance in a L20 volt circuit. When I establish a current through the rods, electric energy is converted into heat by the resistance of the rods. This heat energy is converted into and sent out as radiation, with the exception of the part carried off by heat conduction and convection. Reducing the resistance, I increase the heat, and thereby the radiation from the silicon rods. Still nothing is visible even in the dark. These radiations are of too low frequency, or great wavelength, to be visible. By holding my hand near the rods, I can feel the energy as heat, and show it to you, by bringing the rods near to this Crookes radiometer, which is an instrument showing the energy of radiation. It consists, figure 10, of 4 aluminum vanes, mounted in a moderately high vacuum so that they can move very easily. One side of each vane is polished, the other blackened. The waves of radiation are reflected on the polished side of the vane. On the blackened side they are absorbed, produce heat, thus raise the temperature of the air near the vane. The air expands and pushes the vanes ahead, that is, rotates the wheel. As you see, when I bring the heated rods near the radiometer, the wheel spins around at a rapid rate by the radiation from the rods, which to the eye are invisible. Increasing still further the energy input into the silicon rods, and thereby their temperature, the intensity of radiation increases. But at the same time radiations of higher and higher frequencies appear, and ultimately the rods become visible in the dark, giving a dark red light. That is, of all the radiations sent out by the rods, a small part is of sufficiently high frequency to be visible. Still further increasing the temperature, the total radiation increases, but the waves of high frequency increase more rapidly than those of lower frequency. That is, the average frequency of radiation increases or the average wavelength decreases and higher frequencies appear, orange rays, yellow, green, blue, violet. And the color of the light thus gradually changes to bright red, orange, yellow. Now, I change over from the silicon rods, which are near the maximum temperature they can stand, to a tungsten lamp, a 40-watt 110-volt lamp, connected in series with a rheostat of 2000 ohms resistance in a 240-volt circuit. For comparison, I also turn on an ordinary 16C-P carbon filament incandescent lamp, running at normal voltage and giving its usual yellow light. Gradually turning out the resistance, the light of the tungsten lamp changes from orange to yellow, yellowish white. And ultimately, with all the resistance cut out and the filament running at more than double voltage, is practically white. That is, gives a radiation containing all the frequencies of visible light in nearly the same proportion as exist in sunlight. If we should go still further and very greatly increase the temperature, probably because of the more rapid increase of the higher frequencies, violet, blue, green, than the lower frequencies of light, red, orange, and yellow, with increase in temperature, the light would become bluish. However, we are close to the limit of temperature which even tungsten can stand. And to show you light of high frequency or short wavelength, I use a different apparatus in which a more direct conversion of electric energy into radiation takes place, the mercury arc lamp. Here the light is bluish-green, containing only the highest frequencies of visible radiation, violet, blue and green, but practically none of the lower frequencies of visible radiation, red or orange. In the tungsten lamp at high brilliancy and more still in the mercury arc, radiations of higher frequencies appear, that is, shorter wavelengths than visible light. And these radiations are again invisible. As they are of frequencies beyond the violet rays of light, they are called ultraviolet rays. While the radiations which we produced from the heated silicon rods at moderate temperatures were invisible because of too low frequency and are thus called ultrared rays, or infrared rays, as they are outside of and below the red end of the range of visible radiation. To produce powerful ultraviolet rays, I use a condenser discharge between ion terminals, a so-called ultraviolet arc lamp. 3 iron spheres, I in figure 11, of about 3/8 inch in diameter, are mounted on an insulator B. The middle sphere is fixed. The outer one's adjustable and set for about 3/16 of an inch gap. This lamp is connected across a high-voltage 0.2 microfarads mica condenser C, which is connected to the high-voltage terminal of a small step-up transformer T giving about 15,000 volts, 200 watts. The low-tension side of the transformer is connected to the 240-volt 60-cycle circuit through a rheostat R to limit the current. The transformer charges the condenser, and when the voltage of the condenser has risen sufficiently high it discharges through the spark gaps I by an oscillation of high frequency, about 500,000 cycles. Then charges again from the transformer, discharges through the gap, etc. As several such condenser discharges occur during each half wave of alternating supply voltage, the light given by the discharge appears continuous. You see, however, that this iron arc gives apparently very little light. Most of the radiation is ultraviolet, that is, invisible to the eye. To make it visible, we use what may be called a frequency converter of radiation. I have here a lump of willemite, native zinc silicate, a dull greenish-grey looking stone. I put it under the iron arc and it flashes up in a bright green glare by converting the higher frequency of ultraviolet rays into the lower frequency of green light. This green light is not given by the iron arc, as a piece of white paper held under the arc shows only the faint illumination given by the small amount of visible radiation. I now move a thin sheet of glass, or of mica, between the iron arc and the lump of willemite, and you see the green light disappear as far as the glass casts a shadow. Thus glass or mica, while transparent to visible light, is opaque for the ultraviolet light of the iron arc. A thick piece of crystallized gypsum, selenite, put in the path of the ultraviolet light does not stop it, hence is transparent, as the lump of willemite continues to show the green light. Or a piece of cast glass its blue light. I have here some pieces of willemite in a glass test tube. They appear dull and colorless in the ultraviolet light, as the glass is opaque for this light. I shift them over into a test tube of fused quartz, and you see them shine in the green glare. Quartz is transparent to ultraviolet light. When investigating ultraviolet light, quartz lenses and prisms must, therefore, be used. Still higher frequencies of ultraviolet light than those given by a condenser discharge between ion terminals are produced by a low-temperature mercury arc. Obviously, this arc must not be operated in a glass tube but in a quartz tube, as glass is opaque for these rays. These ultraviolet radiations carry us up to frequencies of about 3,000 times 10 to the 12 cycles per second, or to wavelengths of about 10 times 10 to the -6 of the centimeter. Then, however, follows a wide gap, between the highest frequencies of ultraviolet radiation and the frequencies of X-rays. In this gap, radiations of very interesting properties may sometimes be found. At the extreme end of the scale we find the X-rays and the radiations of radioactive substances, if indeed these radiations are wave motions, which has been questioned. Since at these extremely high frequencies reflection and refraction cease, but irregular dispersion occurs, the usual methods of measuring wavelengths and frequencies fail. The X-rays apparently cover quite a range of frequency and their average wavelength has been estimated as 0.01 times 10 to the minus 6 of centimeter, giving a frequency of 3 times 10 to the 18th cycles per second. In comparing vibrations of greatly differing frequencies, the most convenient measure is the octave, that is, the frequency scale of acoustics. 1 octave represents a doubling of the frequency. N octaves higher then means a frequency 2n times as high, n octaves lower, a frequency a half n as high. By this scale all the intervals are of the same character. 1 octave means the same relative increase, whichever may be the absolute frequency or wavelength. As the perceptions of our senses vary in proportion to the percentual change of the physical quantity causing the perception, Fechner's law. In the acoustic or logarithmic scale, the steps are thus proportional to the change of sensual perception caused by them. The visible radiation covers somewhat less than 1 octave. Ultraviolet radiations have been observed beyond this for about 2 more octaves. 10 octaves higher is the estimated frequency of X-rays. On the other side of the visible range, towards lower frequencies or longer waves, ultra-red rays. Observations have been extended over more than 8 octaves up to wavelengths as great as 0.03 centimeters length, or frequencies of only 10 to 12 cycles per second. The ultra-red rays given by the heated silicon rods of our experiment do not extend to such low frequencies. But such very low frequencies have been observed in the radiations of bodies of very low temperature, as liquid air, or in the moon's rays. 7. Very much longer waves, however, are the electric waves. They are used in wireless telegraphy, etc. I here connect, figure 12, the condenser C of the apparatus which are used for operating the ultraviolet arc, to a spark gap G, one of which the one side is connected to ground B1, the other side to a vertical aluminum rod A1 about 8 feet long. The charge and discharge of the aluminum rod A1 by the oscillating condenser current send out an electric wave of about 50 feet length. This wave passes through you, and when striking the aluminum rod A2 back of you, induces therein an electric charge. A2 is separated from ground B2 by a narrow spark gap G2 between graphite terminals. And the arrival of the electric wave at A2 causes a small spark to jump across the gap G2 which closes the circuit of the tungsten lamp L, thereby lighting it as long as the wave train continues. The electric waves used in wireless telegraphy range in wavelengths from 100 feet or less to 10,000 feet or more, corresponding to 10 to the 7th and 10 to the 5th cycles per second. Still very much longer waves are the fields of alternating current circuits. The magnetic and electrostatic field of an alternating current progresses as a wave of radiation from the conductor. But as the wavelength is very great, due to the low frequency, a 60-cycle alternating current gives a wavelength of 3 times 10 to the 10th divided by 60 is equal to 400 times 10 to the 6th, or 3,100 miles. The distance to which the field of the circuit extends is an insignificant fraction only of the wavelength, and the wave propagation of the field thus is usually not considered. Electric waves of higher frequencies than used in wireless telegraphy are the Hertzian waves, produced by electric oscillators, that is, a moderately long straight conductor cut in the middle by a gap and terminated by spherical condensers, as shown in figure 13. On these waves the velocity of propagation has been measured by Hertz by producing standing waves by combination of main wave and reflected wave. Still much higher frequencies are the oscillations between the cylinders of multi-gap lightning arresters, and the limit of frequency of electric waves would probably be given by the oscillating discharge of 2 small spheres against each other when separated by a narrow gap. It probably is at about 5 times 10 to the 10th cycles, or 0.6 centimeter wavelength. The blank space between the longest electric wave and the shortest ultraviolet light wave thus has become fairly narrow, from 0.6 to 0.03 of a centimeter, or only about 4 octaves. 8. In the following tables, the different known forms of radiation are arranged by their frequency and wavelength, and also given in octaves, choosing as 0 a point the middle C of the piano, or a frequency of 128 cycles per second. These radiations are plotted graphically in figure 14, with the octave as abscissa. As seen, the total range of frequencies of radiation is enormous, covering nearly 60 octaves, while the range of sound waves is only about 9 octaves, from 15 to 8,000 cycles. There are 2 blank spaces in the range of radiation, one between electric and light waves, and a second and longer one between light and X-rays. It is interesting to note that the range of electric waves is far greater than that of light waves. Only a very narrow range of radiation, less than 1 octave out of a total of 60, is visible. It is shown shaded in figure 14. This exhibits the great difficulty of the problem of efficient light production. It means producing as large a part of the total radiation as possible within this very narrow range of visibility. Regarding the range of frequencies covered by it, the eye thus is much less sensitive than the ear, which hears over 8 octaves as sound waves. While the visible radiations are the most important ones, as light, the total range of radiation is of interest to the electrical engineer. The ultra-red rays are those radiations which we try to avoid as far as possible when producing light, as they consume power and so lower the efficiency. The ultraviolet rays are of importance in medicine as germ killers. They are more or less destructive to life, appear together with the visible radiation, and where they are of appreciable amount, as in the arc, protection against them becomes desirable. The X-rays have become of importance in medicine, etc., as they penetrate otherwise opaque bodies and thus allow seeing things inside of other bodies. The total range of electric waves, between the frequencies of alternating currents and the limits of electric waves, has been of importance to the electrical engineer as harmful and destructive phenomena in electric circuits, which are to be guarded against, and only in recent years. With the development of wireless telegraphy, some such electric waves have found a useful commercial application. The main object of their study, which is the study of transient electric phenomena, is still, however, to guard against their appearance in electric circuits and discharge them harmlessly when they appear. Considering the great difference which already exists between alternating currents of low frequency, 25 or 15 cycles, and of high frequency, 133 cycles, and realizing that the total range of waves, which may appear in electric circuits, is many times greater than the difference between high and low frequency alternating currents, it can be realized that the differences in the character of electric waves are enormous between the low frequency surges of near machine frequency and the high frequency oscillations of a multigap lightning arrestor, near the upper limits of electric wave frequencies. And the problem of protecting circuits against them thus is vastly more difficult than appears at first sight, and the conclusions drawn from experimental investigations of electric waves may be very misleading when applied to waves many octaves different from those used in the experiment. This explains the apparently contradictory evidence of many experimental investigations on the protection of electric circuits.